everyone, welcome again. So today we are going to talk about how to test a system that is more or less like, let's say, a virtualization system like QEMU or VirtualBox, etc., etc. So this system is called Gen5, okay? And is able to simulate different architectures. So we can put programs to run, let's say, under x86 or ARM or AMD 64. So we will see how the system works and the main important thing, how we can test it, how we can identify bugs in the system. So we are going to present a system called SearchGem5 that is going to test Gen5, which is the system that I was talking about. And SearchGem5, basically what it's going to do is to try to apply a combination between language models, search algorithms, and fuzzing in order to identify potential bugs in Gen5, okay? So this work is a collaboration between my former colleagues from UCL, Bill and Justina, and also my colleagues from King's, Aidan, Karin, and myself. And the presentation that you are going to see today was created originally by Karin and then modified by me, but basically the work was a companion of everyone's effort. So let's talk about software testing first. So basically you have your program under test, and what you are going to do is to create an input for the program, okay? The testing system will be generating inputs if you are lucky and you have an automatic testing system. Normally we do the test manually. So once you pass the test, you either get an answer that might be wrong or right, okay? And you will try to create a corpus of tests, maybe automatically, maybe manually, just to make sure that you can identify potential bugs in your program. So this test will also have like a historical guarantee that the program is actually right, okay? So let's talk about the system that we want to test, Gen5. So basically, as you can see here, Gen5 is an open source system. It started in August 2021, so it's basically 12 years old, and is mainly written in C++ and Python. So just to give you a little bit about the complexity of Gen5, basically it has 1.34 million lines of code, so you can imagine that it's very, very difficult to test the whole system because you have different architectures, you have different things that you can simulate with and without the operating system, so there are many, many things that still need to be tested, okay? Basically it tries to simulate different hardware which are very complex, different computer architectures, system development, so it's like a very strong effort that requires knowledge from academia and industry. So how we test large systems, okay? So how we can test these specific kinds of systems. So the first approach that is the most obvious will be manual testing. So with manual testing, we can just design the test of what we want to test, and we can just try to reach specific points on the program. But you can imagine the cost of this. You need people writing the test, you need a lot of people, you need knowledge of the program will be changing maybe like every other month, so it's not trivial to do manual testing. Another option from a static analysis perspective is to do maybe model checking or static analysis, which will be something that it would be good, but the problem is that they suffer from false positives. So for example, you can use a certificate compiler like Concert, but it's not completely complete, and you will find limitations in terms of false positives when you are trying to do static analysis, and also the path exploitation problem if you are using, for instance, symbolic execution. So it's good, but still might not be the best solution. So for our approach, what we decided to do is to use testing. So testing can actually deal with the system, it can receive feedback. In this case, we are going to use fuzz-based testing or fuzzing, and basically with that feedback we can guide the testing process through the system. It's not going to be maybe the best solution, but actually it has been successful in many cases. So for instance, for testing Facebook, we have tools that has reached like a lot of interest, like Infer or Sapiens, and you can find a lot of papers based on fuzzing that are actually very successful on testing large systems. So that's the reason we approach this problem through a fuzzing perspective. So what are the specific challenges that we are going to face here with Gen5? As I mentioned, Gen5 is huge. It has 1.34 million lines of code, but at the same time, we have to simulate hardware, which is extremely complex. So we will have inputs that are maybe binary files that have never been generated before for a hardware that has never maybe been used before. So it's something that makes the oracle fuzzy. and we don't really know how the oracle should behave. Nonetheless, basically what we can do is to try to create an environment when we try to identify errors in the simulation system itself, deep errors, instead of just errors in the input-output behavior. But we will see that we also deal with the input-output behavior. We'll see a little bit more about this. But just to go back to the previous diagram when we were doing the testing, in this case, instead of just testing a software under test, what we are going to test is Gen5 in the same way that we are normally testing software under test. So now we have all the challenges, obviously. We need to generate these specific inputs. So how do we do that? No? How do we generate these inputs if we have no idea about the structure of the system, or we have no idea about how the system is going to interact with them? So basically, we are going to start creating the input from a specific seed that we will be mutating. And the mutation is going to be very complex because we need to mutate a binary file, but we need to keep the binary file as a valid file. That sounds very familiar if you know about malware. Basically, why do we care about binary files? So this is to try to reach as much as we can of Gen5. So in this example, you can see that if we try to test just a bunch of binaries that are valid, we will test probably the beginning of Gen5. But a lot of the system is not going to be tested. So our approach is going to focus on this red area that is not tested yet. So what's our approach? What is the main idea behind our approach? So if we focus on the red area of Gen5 that we want to test, we are going to try to reach it in 3 different steps. The first step combines LLMs and AFL. So we will provide a prompt to an LLM. In this case, it's going to be GPT 3.5 that will give us different tests, and with AFL we will be running the test. Nonetheless, this is not going to be enough. I mean, this is going to generate different test cases, but we will need to mutate the test cases. But it will support us to reach the area where we want to actually test Gen5. And once we reach the area, we will start mutating a little bit more. How do we do that? So basically, we will have the corpus of inputs. We will have a fuzzy system that is going to take these inputs, and AFL is going to be working on the AFL++, is going to be working on fuzzing the system, but we will create a custom mutator that allows us to manipulate the binary files. We will talk a little bit more about the custom mutators later. So this custom mutator is going to be feeding AFL, it's going to be trying to reach more coverage of the system that we are trying to test, and basically we will do a whole instrumentation of Gen5. So we will instrument the 1.34 million lines of code in order to receive feedback from the whole system. You can imagine that this process is really slow and it requires a lot of resources, but still is worth it because we can get a lot of information from the system that we are testing. So with this, we will create a fast corpus that will provide us access to that specific region of the system that we haven't not been able to test before. So now, how can we generate the initial binary file? How can we make sure that the binary is actually valid and the test case is something that will be that we can compile? So we will start with basically a little bit of randomness based on LLMs. We will provide a prompt to the LLM that you can just read here. I will give you a set of n programs from a source X. Can you generate a pair per program with an input sample and its type information for the second program? These are the programs, name code. So basically you can see that we will provide like a set of programs that come from specific testing examples of compilers. So these programs are going to be paired. One is going to have no type information and the other one is going to have type information. This is because we want to use the type information for later on manipulating not only the input for Gen5 that is going to be the program, but also the input for the program that we are simulating inside of Gen5. So we will give a broader coverage afterwards. So this is going to become the template of my program, and this is going to be compiled by GCC, and we will use it for generating the binary file. That will be our first step. So now we are going to be able to mutate the input that I was mentioning. So basically the program has the inputs are going to be arguments to the program, and we are going to use just the mutators that AFL has for input. So our custom mutator is going to have this into account. It's going to check the type of the input to make sure that the mutation makes sense. So instead of giving a string to an integer, we are going to be giving actual proper mutations to the file. And this is going to be generating different mutations. So for example, if you have an integer that is originally 5, we will mutate it to 9. And this is going to give us different seeds and different mutators for the system. And this is possible because the LLM is providing us type information about the variables of the specific files. At the same time, we will be doing mutations on the binary itself. So this will allow us to play a little bit more with the binary in order to see how the mutation of the binary code itself is affecting the execution of the program under the simulator, because that will be able to generate some panic examples during the execution. And finally, we will do like a post-fuzzing process that is basically a differential testing approach. This idea is actually really interesting. It was mainly Karim's idea, and it says, okay, yeah, we are doing an execution of the program, and we can put an oracle using differential testing. So we are going to check whether the output of the binary is the same inside of the simulator and outside of the simulator with similar conditions. So if that's the case, everything is good. If that's not the case, there must be something that is not working properly. And that's something that we can also report in the future. So this is basically the part of differential testing that we will be doing in the post-fuzzing. We are going to get the input, we are going to get the simulator and the executing environment, and we are going to cross-check the results. So how did we evaluate this system? So basically, we created a corpus of programs using LLM based on the programs that I mentioned before that are for testing compilers, and we compiled the programs with GCC 11. Then we manipulated also we also generated the input types for these programs, and we manipulated the binaries and the inputs with AFL++. Just to give you a little bit about the numbers, that the number of resources that we needed like a big computer with 72 gigabytes of RAM to be able to deal not only with the instrumentation of Gen 5 but also with the fuzzing campaigns. And our fuzzing campaign lasts 10 days. So it was a very long fuzzing campaign. Okay, let's have a look to the results that we obtained with SearchGem5. So basically we started with a number of tests, a corpus of about 700 tests, and we start generating the mutations and the search process with SearchGem5. Just to give you a little bit of the original numbers from this original test, we have about a 20% that didn't compile, that were generated by the LLM but didn't compile, so we couldn't use them, and also an 8% that were dynamically invalid, so the inputs didn't really run the software. And we have two sides that we were testing. We were testing the input and we were testing the binaries. So when we were doing this, and when AFL was generating new good input pairs of binaries and inputs, basically it was able to generate about 19 of the 72 were basically new inputs that were interesting for the testing, that were increasing the coverage, and also the other 50% were new binaries from the ones that we were able to compile from the LLM. And this generated a new corpus with about 4,005 test cases that were useful to improve coverage on the system. Okay, so from the experiments with bugs we were able to identify. I would like to highlight that we identified 17 different categories thanks to the operations that we were doing either in the binaries or on the inputs. Only one of these categories is also identified by the corpus generated by the LLMs with no modification of SearchGem5. Okay, so we were fuzzing for 10 days. I think I already mentioned this. We have a corpus of inputs of 744 different inputs that will be inputs for the program, and SearchGem5 was able to create 2,136 unique binaries that are the percentage that we were discussing in the previous slide. So which specific crashes or issues we identified when we were manipulating our binary and our constants? So here on the table you have 1 to 7. These errors that are basically manipulations based on the binary or on the context. So you see the B is only on the binary. If you see the C, it's also on the inputs of the binary. Basically, we're focused on errors in specific sections of the code of Gen 5. Some of them were memory sections, some of them were object sections, but mainly all of them were manipulating conditions. However, from number 8, you can see that actually we are going more to the memory maps and to the faults. We also identify crashes on assertions that fail. So for example, assertions inside of Gen5 itself, which means that there must be something that is affecting the system. We identify hands, like in number 13. We identified missimulations. That was expected because it was also identified by the LLM. It's the only error that the LLM is able to identify, number 14, that the program is simulating something that is not supposed to simulate. In number 15, we have another kind of the simulation where the variable's value is random in x86, was fixed in the simulation, and other kinds of crash and missimulations as number 16 and 17, where the 17 is actually the one based on differential testing. So you can see that we have many different types of errors that we can identify thanks to SearchGem5 instead of a single error that will be generated by the LLM. I would like to highlight that in many cases the LLM will be something that close to what a human would do. So we are just complementing these abilities of a human for creating tests by applying search and going deeper inside of the testing process of Gen5. In terms of coverage, we wanted to know how much coverage we were increasing thanks to the mutations that we were doing. So we can see that originally we have about 39,000 lines of code coverage, which is actually quite good with just the LLM. And thanks to the search process, we were able to increase about 1,000 lines of code. It doesn't really look relevant, but considering the errors that we were able to unmask, it's actually quite relevant. And if we will have more resources and maybe more people focus on different architectures and different aspects of the system itself, we will be able to identify even more errors inside of the system. Just to give you a little bit disclosure, we were measuring the cover with GCOV. So just to conclude, we were able to identify 17 different categories of bugs when only with LLMs we were able to identify one category. So we think that actually this was a very successful approach in terms of technical challenge in order to identify bugs in these kind of complex systems. Also, we think that this system is easy to portray to different simulation systems, so this will be part of the things that we want to do in the future. And actually we discovered that this non-deterministic nature of the LLM can be actually very helpful for identifying new bugs in systems because they generate tests in a non-deterministic way. So actually that's good for us because we can identify new bugs inside of programs. Just a small disclosure, you have the code in the QR code that you have in the right side, but in the left side we are looking for people who is interested on apply it to the ECOP artifact evaluation. So if you want to self-nominate yourself, please just follow the link. Thank you very much, and I hope you enjoyed the presentation. Thank you. Bye-bye.